Tonight I want to explore something that quietly unsettles astronomers, not out of fear but out of genuine puzzlement. Because when we look into the universe with ever greater clarity, we are finding things that simply refuse to fit. Objects and signals that contradict our expectations. Phenomena that, according to everything we think we understand, should not be there at all. These are not ideas pulled from science fiction, nor are they speculative thought experiments. They are real observations, measured, recorded, verified. They exist out there in the cosmos right now, behaving in ways we cannot yet explain. Over the last few decades, as our instruments have grown more sensitive and our reach into the universe has extended, we have encountered discoveries that leave even the most experienced scientists quietly baffled. Some of these findings push at the edges of known physics. Some hint that there may be processes at work in the universe that we have not yet imagined, and some, quite frankly, are simply strange. So let us step into one of these mysteries beginning on August 15th, 1977. On that day, data from the Big Ear radio telescope at Ohio State University was being examined. This telescope was part of the search for extraterrestrial intelligence, a project designed to listen for radio signals that might betray the presence of intelligent life beyond Earth. Each day, the telescope swept the sky, collecting vast streams of data. Most of it was unremarkable, just the steady hiss of cosmic background noise, the ordinary radio chatter of the universe. But on this particular day, something extraordinary appeared. Buried in the data was a signal so unusual that it demanded attention. It stood out sharply against the background, prompting an immediate reaction and a single word written beside it. That is how it became known as the wow signal. The signal persisted for 72 seconds. During that brief window, it was roughly 30 times stronger than the surrounding background noise. It appeared to originate from a specific region of the sky in the direction of the constellation Sagittarius. And here is where the mystery deepens. The frequency of the signal was close to 1,420 megahertz. This is significant because that frequency lies very near the hydrogen line, a natural emission frequency associated with hydrogen atoms. Hydrogen is the most abundant element in the universe. If an intelligent civilization wished to broadcast a signal that others might notice and recognize, choosing a frequency tied to hydrogen would make a certain kind of sense. It would be a universal marker, grounded in the shared physics of the cosmos. The Big Ear telescope used 2 receivers to scan the same region of sky, separated by about 3 minutes. The signal appeared clearly in the first receiver, but it was absent in the second. That tells us it did not last long, almost certainly less than 3 minutes, and most likely close to the observed 72 seconds. Since 1977, astronomers have returned to that exact region of the sky again and again. They have listened with far more powerful instruments. They have searched at the same frequency and at neighboring frequencies. They have looked for any hint that the signal might repeat. Nothing has ever been detected. The wow signal remains a singular event, never observed again. It is important to be honest about what we do not know. The signal could have had a natural origin, or it could have been artificial. The telescope itself was not capable of pinpointing the source with high precision, so we are left with only a general direction, not a specific object. Several natural explanations have been proposed. One idea suggests a passing comet. When the solar wind interacts with the cloud of hydrogen surrounding a comet, radio emissions can be produced. Years later, it was suggested that 2 known comets may have been passing through that region of space at the time the signal was detected. But there is a significant problem with this explanation. The signal was extremely narrow in bandwidth. It occupied a very precise frequency, far more precise than what we would normally expect from a natural source like a comet. Natural sources tend to spread their signals across a wide range of frequencies. What made the wow signal so striking was its extreme narrowness, a characteristic far more in line with something artificial, a transmission deliberately placed on a precise frequency. Some scientists have argued that it may have been interference originating from Earth, perhaps a satellite, an aircraft, or even a ground-based transmitter that happened by chance to align perfectly in time and frequency. Yet the Big Ear telescope was specifically engineered to eliminate terrestrial interference, and the signal arrived from a region of the sky that did not match the position of any known satellite or aircraft at that moment. So what was it? Quite simply, we do not know, and that uncertainty is exactly what gives it such power. Almost 50 years on, the wow signal remains one of the most compelling unsolved observations in the entire history of the search for extraterrestrial intelligence. The fact that it was never detected again is both deeply frustrating and profoundly important. If it truly originated from an alien civilization, why would it appear only once? Perhaps they were employing a lighthouse-like strategy, sweeping a focused beam across the galaxy, and for 72 seconds, Earth happened to lie in its path. Perhaps it was a single intentional broadcast. Perhaps it was never intended for us at all. It could have been nothing more than accidental leakage from another form of communication. Or perhaps it had nothing to do with intelligent life whatsoever. The universe is teeming with natural processes that generate radio waves, pulsars, quasars, magnetars, and the remnants of supernova explosions. We are still uncovering entirely new classes of radio sources. It is possible that the WOW signal was produced by some natural phenomenon we have yet to understand, something we have never observed before or since. The truth is, we may never know. The signal lasted 72 seconds in 1977 and then vanished, never to return. It is a mystery locked in time. But it also serves as a powerful reminder of just how much of the universe remains unexplained. Somewhere in the direction of Sagittarius, something emitted a strong, narrow band, radio signal, and by pure chance we detected it. That is either the most astonishing coincidence in the history of astronomy, or it is evidence of something truly extraordinary. Either way, it is profoundly strange, and that is why nearly 5 decades later, the WOW signal continues to captivate our imagination. Now let us turn to something unfolding in our own time, a star that has puzzled astronomers since 2011. Its catalogue name is KIC 846285, though it is more commonly known as Tabby's star, named after astronomer Tabitha Boyajian, who led the team investigating it. Tabby's star lies about 1,460 light-years from Earth in the constellation Cygnus. At first glance, it appears entirely unremarkable. It is slightly larger and slightly hotter than our Sunday. There is nothing about it that should draw special attention. And yet in 2011, the Kepler Space Telescope detected something deeply unusual. Stars do dim from time to time, and that is perfectly normal. When a planet crosses in front of a star from our point of view, the star's brightness dips slightly. This is how we discover exoplanets. If Earth passed in front of the Sun as seen from another star, the Sun's light would drop by about 0.01%. It is a tiny change, but one we can measure. A much larger planet like Jupiter would cause the Sun to dim by roughly 1%. That is the kind of regular, predictable, modest dimming we expect from planets. Tabby's star behaves nothing like that. In 2011, its brightness plunged by 15% and then recovered. In 2013, it dropped by 22% and then returned once more. These dimming events were irregular. They did not repeat on a fixed schedule. They lasted for different lengths of time. Sometimes the star faded slightly, sometimes dramatically. A 22% drop is enormous. That cannot be caused by a planet. Even a planet as large as Jupiter would block only about 1% of the star's light. To obscure 22%, you would need something truly colossal, something approaching the scale of the star itself. The discovery sparked a wave of speculation. What could possibly be blocking that much light? And this is where the story took a remarkable turn. One proposal was that we might be seeing an alien megastructure. The idea is rooted in a theoretical concept known as a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson asked what a highly advanced civilization might do when its energy demands became immense. His answer was that such a civilization might eventually build vast structures around its star to harvest its energy output. Not a solid shell, which would be physically impossible, but a swarm of energy collecting satellites orbiting the star. If something like that were under construction, it would block different amounts of starlight at different times as the swarm moved. The dimming would be irregular. The drops in brightness would be large. And observationally, it would look very much like what we were seeing from Tabby's star. Now, before imagination runs too far, it is important to be clear. The vast majority of astronomers do not believe Tabby's star hosts an alien megastructure. That idea was always the least likely explanation. But it was considered seriously because at the time no other explanation fit the data. That is just how strange this star appeared. So, if it is not aliens, then what is it? Scientists began proposing a range of natural explanations. Perhaps there is a vast swarm of comets moving around the star. If a whole family of comets happen to drift across our line of sight, they could interrupt the starlight in an uneven way. Their dusty tails would not block light smoothly, but in irregular patches, producing the strange dips we observe. For a time, this idea sat at the forefront of scientific discussion, yet it quickly runs into serious difficulties. Where could such an immense population of comets originate? To obscure 22% of the star's light, you would require an almost unimaginable number of them. There is another issue. Comets generate dust, and dust alters light. When starlight passes through it, the star should appear redder during periods of dimming. That is not what we see. With Tabby's star, the color remains essentially unchanged, even as the brightness drops. Another proposal followed. Perhaps a recent collision had taken place. If two large bodies smashed together close to the star, the expanding cloud of debris might block the light in an irregular fashion as it spread. But once again, the evidence does not cooperate. Warm dust from such a collision should glow in infrared light, producing a clear excess signal. We do not detect that. Some researchers then turn their attention back to the star itself. Maybe the star is variable, naturally changing its brightness over time. Yet Tabby's star does not behave like known variable stars, and the pattern of dimming is far too erratic to fit that explanation. Then in 2017, astronomers made a crucial observation. They caught the star dimming again, this time measuring it across multiple wavelengths of light. What emerged was intriguing. The dimming was stronger in blue light than in red light. That behavior is exactly what you would expect if dust were blocking the starlight. Tiny dust grains scatter blue light more efficiently than red light. It is the same physical process that gives Earth its blue sky. So perhaps dust really is involved after all. But that simply opens a new set of questions. Where is this dust coming from? Why is there so much of it? And why does it produce such an unpredictable pattern? The most recent observations suggest that Tabby's star may be surrounded by a vast field of debris, possibly the remains of a shattered planet, a colossal collision, or some other catastrophic event. As this material orbits the star, it blocks the light in a chaotic way. This is the leading explanation today, but it is deeply unsatisfying. The full picture still eludes us. And what makes the story even more extraordinary is that the behavior continues. We have now observed this star for more than a decade. It keeps dimming in strange and unpredictable ways. Multiple telescopes, multiple data sets all tell the same story. This is not an error. It is not a faulty instrument. Something real is interfering with the light from this star, and we do not yet understand what it is. As of 2025, Tabby's star remains one of the most baffling objects in the sky. Among hundreds of billions of stars, it stands alone. Nothing else behaves quite like it. Perhaps one day we will uncover a natural process we have simply never encountered before. Or perhaps it is something entirely different, something that has not yet occurred to us. Let me now turn to another discovery that challenges our expectations just as profoundly. In 2019, scientists identified objects that by all rights should not exist. They are known as odd radio circles, or OCs. The name could not be more fitting. They are strange, they are circular, and we can see them only at radio wavelengths. Here is what happens. Aim a radio telescope at certain regions of the sky, and a perfect circle appears. These circles are enormous, stretching across hundreds of thousands of light years, and at their centers more often than not sits a galaxy. The first examples emerged during a survey of the radio sky, conducted with the Australian Square Kilometre Array Pathfinder telescope, known as ASCAP. This instrument is exquisitely sensitive to radio waves, revealing a universe that optical telescopes simply cannot see. When the data were processed, these circular structures stood out immediately. At first, they were dismissed as artifacts. In astronomy, perfect circles raise suspicion. Nature rarely draws with such precision, but careful checks confirmed that the circles were real. More were found, and independent observations verified them. As of 2025, roughly a dozen OCs are known. They are rare, vast, and their origin remains mysterious. What exactly are we seeing? Each OC appears as a ring or shell of radio emission, often almost perfectly circular. At the center typically lies an elliptical galaxy that looks entirely ordinary in visible light. There is nothing about it that obviously explains the immense radio ring surrounding it. Some of these rings exceed 1 million light-years in diameter, about 10 times the width of the Milky Way. These are structures on an almost unimaginable scale. Astronomers are familiar with circular forms in the cosmos. Supernova remnants, the expanding shells left behind by exploding stars, can look round, but those remnants are far smaller and tied to recent stellar deaths. OCs are far too large and too distant to fit that category. Planetary nebulae can also appear circular formed when dying stars shed their outer layers, yet those too are small and confined to our own galaxy. OCs are clearly something else. There are also galaxies with radio lobes where jets from a central black hole blast material into space, sometimes producing circular shapes when viewed from certain angles. But OCs do not match these systems either. The central galaxies show no signs of the active supermassive black holes required to generate such immense radio structures. And so once again, we are left staring at the universe, confronted with something real, something vast, and something we do not yet understand. So what then are these things? The honest answer is that we simply do not yet know. Scientists have put forward a range of ideas. One possibility is that they are vast shock waves born from titanic explosions in the hearts of galaxies. If a galaxy experienced a prolonged burst of star formation, or if the supermassive black hole at its center suddenly switched on, that release of energy could drive a powerful blast wave expanding steadily into intergalactic space. Over millions of years, such a wave might form an immense, roughly spherical shell that glows in radio light. But if this explanation is correct, it immediately raises a puzzle. Why do we not see many more of them? Galaxies enter active phases quite frequently on cosmic timescales. If this process were common, these structures should be everywhere, yet they are not. Another idea links them to galaxy mergers. When galaxies collide, the physics becomes extraordinarily violent and complex. Perhaps those collisions generate shock fronts that propagate outward, eventually forming giant spherical shells. But again, galaxy mergers are not rare events. These objects are. Some researchers have ventured even further, suggesting more exotic origins. Maybe what we are seeing are the fossil imprints of events from the very early universe itself. Perhaps they are connected to cosmic strings, or some other unusual feature woven into the fabric of space-time. These ideas for now remain highly speculative. The reality is that we are still very much at the beginning of understanding these objects. We have only been aware of them for a few years. What we need are more observations. We need to discover more examples. We need to examine the galaxies at their centers in far greater detail. What makes these objects so compelling is that they represent something genuinely new. Astronomers have been mapping the radio sky for decades, yet these structures only emerged when our radio telescopes became sensitive enough. They were always there. We simply lacked the capability to detect them. That tells us something profound about astronomy itself. The universe is overflowing with phenomena we have not yet uncovered, not because they are concealed, but because our instruments have not been adequate to reveal them. Each time we build a more powerful telescope or observe the cosmos in a new wavelength, the universe surprises us. These objects are a perfect illustration of that truth. No one predicted them. No one set out to search for enormous radio circles surrounding galaxies. They appeared entirely unexpectedly. Now astronomers are left with the task of understanding what they are and what they can teach us about the universe. As of 2025, these objects remain unexplained. We know that they exist. We have a broad sense of their appearance, but we do not yet understand what creates them. They are strange features in the radio sky, waiting patiently for an explanation. And now let us turn to something that challenges the rules on a truly cosmic scale. In 2021 and 2024, astronomers identified two colossal structures that call into question one of the most fundamental assumptions in cosmology. The first is known as the Giant Arc. It was discovered by Alexia Lopez, then a doctoral student at the University of Central Lancashire. The Giant Arc is a vast arrangement of galaxies stretching across about 3.3 billion light-years. That figure does not describe its distance from us. It describes its actual size. The structure itself spans 3.3 billion light-years. To grasp the scale of that, consider that light would take 3.3 billion years to travel from one side of this structure to the other. The entire observable universe measures only about 93 billion light-years across. This single structure accounts for a substantial fraction of that span. The Giant Arc lies roughly 9.2 billion light-years from Earth. On the sky, it appears as a sweeping, curved chain of galaxy clusters, resembling an enormous arc, which is how it earned its name. Then, in 2024, the same team uncovered something else. They call it the Big Ring. This is another immense structure, measuring about 1.3 billion light-years in diameter. It is also located around 9.2 billion light-years away. And here is the striking part. It appears in the same region of the sky as the Giant Arc. That means we have two enormous structures occupying the same part of the universe at essentially the same distance. That is difficult to ignore. It hints that they may somehow be connected. So why does this matter? To understand that, we need to talk about a cornerstone of cosmology known as the cosmological principle. This principle states that if you observe the universe on sufficiently large scales, it should look roughly the same everywhere. No matter which direction you look, the overall density of matter should be similar. In other words, the universe should be homogeneous and isotropic when viewed on the largest scales. This assumption underpins our standard model of cosmology. It is strongly supported by observations of the cosmic microwave background, which reveal that the early universe was astonishingly uniform. The giant arc and the Big Ring put this idea under strain. They are simply too large. Calculations based on the standard model suggest that cosmic structures should not grow beyond about 1.2 billion light-years. That limit arises from how long gravity has had to pull matter together since the Big Bang. The giant arc is nearly 3 times larger than that threshold. Even the Big Ring at 1.3 billion light-years is pressing against the edge of what theory allows. If these structures are real, and the evidence suggests that they are, then either our theoretical limits are incomplete, or something unexpected is happening. Perhaps the cosmological principle does not apply as cleanly as we thought. Perhaps the universe is more uneven than we assumed, or perhaps there are physical processes at work that we do not yet understand, capable of assembling structures on scales that theory says should not exist. Some astronomers have wondered whether these apparent formations are genuinely physical or merely statistical tricks of the eye. When we examine the large-scale distribution of galaxies, patterns can sometimes emerge that are not truly meaningful. The human brain is exquisitely tuned to search for order. You begin to link points together to trace lines and curves, and suddenly a chain or an arc of galaxies seems to appear, even if it is nothing more than chance. But Alexia Lopez and her colleagues approached this with rigorous statistical care. When they ran the numbers, the likelihood that the giant arc is simply a random alignment turned out to be about 1 in 6,000. That is a very small probability. It strongly suggests that the structure is real. The statistics associated with the Big Ring are even more persuasive, and crucially, the fact that both of these features occupy the same region of space makes coincidence far less plausible. So what could they be? One idea connects them to something known as baryon acoustic oscillations. In the early universe, sound waves rippled through a hot, dense plasma. As the universe expanded and cooled, those waves left an imprint on the distribution of matter. They set a preferred scale, a characteristic size at which structures tend to form. But the giant arc and the Big Ring do not fit that pattern. Their sizes are far larger than what baryon acoustic oscillations would predict. Another possibility is even more exotic. They may be linked to cosmic strings. These are hypothetical one-dimensional defects in space-time, predicted by certain theories of fundamental physics, but never directly observed. If cosmic strings exist, they could act as seeds for structure guiding galaxies to form along immense thread-like features stretching across the universe. The problem is that cosmic strings remain speculative. We have no direct evidence that they are real, which brings us to the most unsettling possibility of all. It may be that our cosmological model is incomplete. Perhaps the cosmological principle, the idea that the universe is uniform and the same in all directions on large scales, is not as solid as we once believed. Perhaps there are vast structures in the cosmos that our current theories do not fully account for. On the largest scales, reality may simply be more intricate than our models suggest. This would not mean that the Big Bang theory is wrong. It would mean that our understanding of how structure emerged from those early conditions needs refinement. That is the essence of science. We observe, we build models, and when observations no longer fit, we revise our ideas. As of 2025, the giant arc and the Big Ring remain the subject of debate. Some astronomers are convinced they are real structures that challenge the cosmological principle. Others remain cautious, suggesting they could still be statistical anomalies or misreadings of complex data. What is undeniable is that on the largest scales, the universe appears to be more complex than we once imagined. And these colossal features, whether they ultimately prove to be genuine anomalies or something else entirely, are forcing us to rethink how the cosmos is arranged. To see this complexity from another angle, consider a place in the universe that is almost empty. It is known as the Boötes Void, and it is one of the strangest features in the cosmic landscape. The Boötes Void is a region of space roughly 330 million light-years across. To put that into context, it is more than 3,000 times the diameter of the Milky Way. It is an enormous expanse. What makes it so peculiar is what is missing. Based on the average density of galaxies in the universe, a volume this large should contain around 2,000 galaxies. Yet when astronomers survey the Boötes Void, they find only about 60. Almost everything else is absent. It is not entirely empty. A few dozen galaxies are scattered through it, but compared with expectations, It is astonishingly devoid of matter. That is why we call it a void. The Boötes void was discovered in 1981 by the astronomer Robert Kirshner and his collaborators. While mapping the distribution of galaxies, they noticed an immense, seemingly empty region in the direction of the constellation Boötes. At first, there was uncertainty. Perhaps the void was an illusion created by the limitations of the survey. Maybe galaxies had been missed, or the detection techniques were less effective in that part of the sky. But subsequent observations removed the doubt. The void is real. There truly is a vast bubble of space with very few galaxies inside it. Voids themselves are not unusual. The universe has a structure often described as a cosmic web, with filaments of galaxies surrounding large, empty regions. Most voids span tens of millions of light years and are relatively common. The Boötes void, however, stands apart. It is far larger than a typical void. It is one of the biggest known supervoids in the nearby universe, and its existence raises profound questions about how cosmic structure came to be. The universe began in a state that was almost perfectly uniform. The cosmic microwave background shows us that about 380,000 years after the Big Bang, matter was distributed nearly evenly throughout space. There were tiny variations in density, but they were extraordinarily small. Over billions of years, gravity amplified those minute differences. Regions that were slightly denser than average pulled in more matter, growing ever denser as the universe evolved. Regions that began just a little less dense than their surroundings gradually surrendered their matter to nearby areas, and over time turned into vast cosmic voids. When we run computer simulations of this process, something extraordinary happens. The familiar large-scale structure of the universe appears almost by itself. Filaments stretch across space, clusters gather at their intersections, and immense empty regions open up in between, all as a natural consequence of gravity acting on tiny initial differences in density. But these simulations also tell us something important. There are limits. Given the age of the universe and the strength of gravity, voids cannot grow without bound. The Boötes void sits right up against that theoretical boundary. It is almost as large as a void can possibly be. That alone makes it fascinating because it represents an extreme case. It pushes our understanding of how structure forms in the universe. If our models are right, we should not expect to find voids significantly larger than the Boötes void. If we did, it would imply that something fundamental in our theories is missing or wrong. At present, the Boötes void remains just within those theoretical limits, but it is uncomfortably close to the edge, and that is precisely why it deserves such careful attention. There is another intriguing feature as well. The small number of galaxies that do exist inside the void are unusual. Some are forming stars at surprisingly high rates. Others show odd shapes or unexpected properties. It is tempting to think that isolation itself has altered their evolution. Consider what life is like for a galaxy in a crowded region of the cosmos. It is constantly interacting with its neighbors, tugging on them gravitationally, occasionally colliding and merging, exchanging gas forever, shaped by a busy and chaotic environment. But a galaxy inside the Boötes void lives a very different existence. Its nearest neighbor may be millions of light years away. It evolves alone, free from the relentless gravitational disturbances that galaxies in dense regions must endure. This solitude may change everything. Perhaps such galaxies are able to hold on to their gas because nothing strips it away. Perhaps their star formation follows a different rhythm. Perhaps entirely unusual characteristics emerge. The galaxies inside the Boötes void offer us a rare opportunity to study what happens when galaxies evolve in near isolation. It is a natural experiment arranged by the universe itself. And yet the most fundamental question remains unanswered. Why is the Boötes void so empty in the first place? Why did this region of space end up with so few galaxies at all? The most likely explanation reaches all the way back to the beginning. This part of the universe must have started with a slightly lower density than average. Over billions of years, gravity steadily pulled matter out of the region toward denser surroundings, sculpting the vast emptiness we observe today. But that only shifts the mystery back one step. Why was this region less dense to begin with? That question takes us to the very earliest moments of cosmic history. Most cosmologists believe these initial density differences arose from quantum fluctuations during the inflationary epoch, a brief moment of extraordinarily rapid expansion immediately after the Big Bang. These fluctuations were random. Some regions emerged a little denser, others a little emptier. Most differences were tiny, but occasionally, purely by chance, a larger variation would appear. The Boötes void may be the amplified legacy of one of those rare fluctuations. It is astonishing to reflect on this. The immense emptiness we see today, spanning about 330 million light-years, began as a minuscule quantum irregularity in the first fraction of a second after the Big Bang. Over 13.88 billion years, that microscopic imbalance was stretched and magnified into one of the largest voids in the observable universe. This is one of the universe's great lessons. Given enough time, the smallest things can shape the grandest structures. And speaking of the early universe, there is another deeply puzzling feature that has captured the attention of cosmologists. It lies in the cosmic microwave background and is known as the CMBB cold spot. It has been a source of debate since its discovery in 2003. The cosmic microwave background, or CMBB, is the afterglow of the Big Bang itself. When the universe was about 380000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen. Before this moment, the universe was opaque with photons constantly scattered by free electrons. Afterward, space became transparent, allowing light to travel freely for the first time. The CMBB is made of those very photons, which have been journeying across the cosmos for 13.8 billion years. Today, we detect them as a faint microwave glow arriving from every direction in the sky. What makes the CMBB so remarkable is its uniformity. Measure its temperature in one direction and then another, and you find almost exactly the same value everywhere, about 2.725 Kelvin, just a few degrees above absolute zero. But it is not perfectly smooth. Tiny variations exist. Some regions are slightly warmer, others slightly cooler, with differences of roughly 1 part in 1,000,000. These subtle variations are profound. They are the fingerprints of density fluctuations in the infant universe. Regions that were slightly denser left slightly cooler imprints in the CMBB. Over cosmic time, those denser regions grew under gravity, eventually forming the galaxies and clusters we observe today. In this way, the CMBB is an extraordinary relic. It is a snapshot of the universe at just 380000 years old. By carefully studying its delicate pattern of warm and cool spots, we gain direct insight into the initial conditions that shaped everything we see around us now. Satellites such as COBE, WAP and Plunk have mapped the cosmic microwave background in extraordinary detail, and when scientists began to study those maps carefully, they noticed something deeply unexpected. There is a patch of the sky roughly 10 degrees across that is markedly cooler than our theories predict. This feature is known as the cosmic microwave background cold spot. It is not merely a subtle dip in temperature, but about 70 millionths of a degree cooler than the average background. That may sound insignificant, but within the context of the cosmic microwave background, where temperature variations are incredibly small, it is enormous. This cold region lies in the direction of the constellation Eridanus. Its shape is oval, stretching roughly 10 degrees by 5 degrees across the sky, which is about 50 times the apparent size of the full moon. And here is where it becomes truly intriguing. Using our standard model of cosmology, we can estimate how likely it is for a region this large and this cold to arise purely by chance. That probability turns out to be about 2%. Not impossible, but certainly unlikely. A 2% probability means that if you could run the universe 100 times with random initial conditions, you would expect to see a cold spot like this in only about 2 of those universes. We, of course, live in just one universe. So either we are simply unlucky and happen to inhabit one of those 2% cases, or there is something genuinely unusual about this cold spot. Several explanations have been put forward. One leading idea is that the cold spot is caused by a supervoid. Voids are vast regions of space that contain very few galaxies. If there were an enormous void between us and the cosmic microwave background in this particular direction, then photons traveling through it would lose energy through a mechanism known as the integrated Sachs-Wolf effect. The idea works like this. As photons enter a void, they climb out of a gravitational well and lose energy. As they exit the void, they fall back into a gravitational well and regain energy. If the universe were not expanding, these two effects would cancel perfectly. But because the universe is expanding, the void becomes larger and less dense, while the photons are passing through it. As a result, the photons gain slightly less energy on the way out than they lost on the way in. The net effect is that they emerge cooler. In principle, then, a supervoid could produce a cold spot in the cosmic microwave background, and indeed astronomers have found evidence for a large void in the direction of the cold spot. It is not as vast as the Boötes void, but it is still significant. However, there is a serious problem. Even accounting for this void, the calculations show that it can explain only a fraction of the observed temperature drop. To reproduce the full coldness of the spot, the void would have to be unimaginably large, and there is no evidence that such a structure exists. Another far more exotic idea is that the cold spot might be the scar left by a collision between our universe and another universe in a multiverse. In certain versions of cosmic inflation theory, our universe is just one bubble within an infinite froth of universes. If another bubble universe collided with ours very early on, it could leave an imprint in the cosmic microwave background, a circular region that is either colder or warmer than average. This is a highly speculative explanation, and there is no direct evidence for it beyond the cold spot itself. But the fact that scientists are willing to seriously discuss such ideas shows just how perplexing this anomaly is. Conventional explanations struggle to account for it fully. A third possibility is that the cold spot is simply a statistical fluke. A 2% probability means it is rare but not impossible. Perhaps we just happen to live in a universe where this unlikely feature exists. After all, rare things do happen. The difficulty is that we have only one cosmic microwave background to study. We cannot repeat the experiment. We cannot generate 100 universes and see how many of them contain a cold spot. We are limited to a single data point, the universe we inhabit. That makes it extremely hard to determine whether the cold spot is a profound clue or merely an accident of chance. If we could observe 10 universes and found that 9 of them lacked a cold spot, we could be confident that the one in our universe was truly significant. But we do not have that luxury. As of the year 2025, the cosmic microwave background cold spot remains unexplained. It may be partly caused by a supervoid, but almost certainly not entirely. It may be a statistical fluke, though, that feels unsatisfying. It may hint at exotic new physics, but that remains highly speculative. What is clear is that it is anomalous. It stands out sharply in the maps of the cosmic microwave background. It is larger and colder than our models predict. And until we find a compelling explanation, it remains one of those unsettling features of the universe that reminds us how much we still do not understand. Now let us turn to a star that appears to defy the rules of nuclear physics, or at least seems to. It is known as Przylski's star, officially designated HD 1065. It lies about 370 light-years away in the constellation Centaurus. From afar, Przylski's star appears perfectly ordinary. It is an A-type star, roughly twice the mass of the Sun and about 6 times more luminous. On the surface, there is nothing remarkable about it. But when astronomers examined its light spectrum in detail, they encountered something profoundly strange. The star contains elements that should not persist in any stellar atmosphere for more than a few weeks. In particular, it contains technetium, promethium, and other radioactive elements with very short half-lives. To understand why this is such a puzzle, we need to consider how stars make elements. In their cores, stars fuse hydrogen into helium. In more massive stars, helium can fuse into carbon and oxygen. In the most massive stars of all, this process continues building heavier and heavier elements up to iron. Elements heavier than iron are forged during supernova explosions and other extremely energetic events. When a massive star explodes, the immense pressures and temperatures create these heavy elements and scatter them into space. Over time, they become part of the clouds of gas that form new stars. So when we observe heavy elements in a star's atmosphere, we usually assume they were present when the star was born, inherited from previous generations of stars. But there is a crucial complication. Some of these heavy elements are radioactive, which means they decay over time. Uranium, for example, has a half-life of about 4.5 billion years. That means half of any given amount of uranium will decay into lighter elements over 4.5 billion years. Even so, after billions of years, some uranium can still remain. Technetium, by contrast, is a profoundly unstable element. It has no stable isotopes at all. Every version of technetium is radioactive. The most long-lived isotope we know of, technetium-98, survives for roughly 4.2 million years before half of it decays. On the scale of the universe that is a fleeting moment, Przylski's star by comparison is likely billions of years old. Everything we know about its properties tells us it is an evolved, mature star, not one that formed recently. If technetium had been present in its atmosphere when the star was born, every last atom should have vanished billions of years ago. There should be no trace of it today. And yet, when astronomers examine the star's spectrum, they see unmistakable signatures of technetium. Alongside it, they also detect promethium, another radioactive element with an even shorter half-life. Most astonishingly of all, these signals have been observed consistently ever since the star was first studied in depth in the 1960s. So the obvious question arises, where is this technetium coming from? There are a handful of ideas, but none of them sit comfortably with what we think we know. One possibility is that the star is somehow manufacturing technetium at its surface through an unknown nuclear process. Perhaps there exists a mechanism not yet discovered capable of creating these elements in the star's outer layers. But this explanation strains credibility. Nuclear physics is a mature science, and there is no known process that could generate technetium in the relatively cool atmosphere of a star like this. Another suggestion is that the technetium is being dredged up from deep within the star. Conceivably, nuclear reactions in the interior could be producing technetium, which is then carried to the surface by convection. But here too the idea falters. The internal temperatures of the star are simply not high enough to create technetium through standard nuclear reactions. Then there is a third idea, one that feels almost like science fiction. It proposes that the star contains super heavy elements with atomic numbers far beyond anything we have ever observed naturally. In theoretical nuclear physics, there is a concept known as the island of stability. The idea is that if you climb far enough up the periodic table past all known elements, you might encounter a region where certain super-heavy nuclei are unexpectedly stable. If such elements exist, some of them could decay slowly into technetium or promethium as intermediate products. In that case, the star might be quietly replenishing its supply of these radioactive elements over time. This idea is highly speculative. We have never seen super-heavy elements occurring naturally. A few have been created in particle accelerators, but they decay almost immediately. The island of stability remains a theoretical prediction, not an established reality. And yet, Przybylski's star is so extraordinary that astronomers are prepared to entertain even the most exotic explanations. Its strangeness does not end there. The chemical makeup of the star is deeply unusual. It contains remarkably high concentrations of certain rare earth elements. Its spectrum is dominated by strong lines from elements such as holmium, dysprosium, and europium. These elements appear in far greater abundance in Przybylski's star than they do in the Sunday. This places it in the category of chemically peculiar stars. There are several classes of chemically peculiar stars, and they are thought to arise because of processes in their atmospheres. Radiation pressure and magnetic fields can cause some elements to rise while others sink, leading to strange and uneven chemical patterns. But even by those standards, Przybylski's star stands apart. Its abundance patterns are more extreme than almost any other known star, and the presence of short-lived radioactive elements is entirely unique. Some astronomers have wondered whether the star might have a companion. Perhaps it belongs to a binary system with a neutron star, or a white dwarf, and material from that companion is falling onto Przybylski's star, carrying radioactive elements with it. But there is no evidence to support this. The motion of the star shows none of the subtle wobble that would betray the presence of an orbiting partner. As of 2025, Przybylski's star remains an unresolved mystery. For more than 60 years, astronomers have been watching it. For more than 60 years, its spectrum has stubbornly displayed technetium and promethium. By every expectation, these elements should have disappeared long ago, and yet they persist. Either there is a nuclear process at work that we do not yet understand, or the star contains some form of exotic matter, or there is a fundamental flaw in our observations or in the way we interpret them. None of these possibilities is entirely satisfying. That is precisely why Przybylski's star remains one of the most enigmatic objects in the sky. On October 19, 2017, astronomers, using the Pan-STARRS telescope in Hawaii, noticed something unusual moving through the solar system. At first, it was assumed to be an ordinary comet or asteroid, but as more data came in, it became clear that this object was something altogether different. They gave it the name Oumuamua, a word from the Hawaiian language that means scout or messenger, and it became the first confirmed interstellar object ever observed passing through our solar system. Oumuamua arrived from beyond the gravitational domain of the Sun, emerging from true interstellar space. It came in from the direction of the constellation Lyra, swept through the inner regions of the solar system, and then continued its journey back out into the darkness between the stars. We had only a brief window, just a few weeks to observe it before it faded beyond the reach of our telescopes. In that short time, what we discovered was both captivating and deeply puzzling. Oumuamua was unusual in ways that challenged our expectations. To begin with, its shape. By measuring how its brightness changed as it rotated through space, astronomers inferred that Oumuamua was extraordinarily elongated. The best estimates indicated a length of around 400 meters and a width of only about 40 meters, giving it a ratio of 10:1. That suggests a form reminiscent of a cigar, or perhaps something closer to a flattened pancake depending on its exact structure. This is highly uncommon. Most asteroids and comets tend to be roughly spherical or irregular, not stretched into long, slender shapes. Such an elongated body is not impossible, but it is rare. Then there was its surface. Oumuamua appeared reddish, much like certain objects found in the outer reaches of our solar system. This coloration implied prolonged exposure to cosmic radiation, which can alter and darken surface materials over immense spans of time. Up to that point, nothing seemed particularly extraordinary. But there was a crucial difference. Oumuamua showed no evidence of a coma. When comets approach the sun, their icy surfaces heat up and begin to vaporize, producing a surrounding cloud of gas and dust known as a coma. This is what gives comets their familiar glowing appearance. Oumuamua, however, displayed no such feature. Even as it passed remarkably close to the sun, well within the orbit of Mercury, there was no visible coma at all. This strongly suggested that it was not a comet, at least not a conventional icy one. Perhaps it was more akin to an asteroid composed primarily of rock or metal. But then came the most perplexing observation of all. Oumuamua's path through space did not behave exactly as our models predicted. After it passed the sun and began heading back out of the solar system, it was accelerating slightly more than it should have been. When we calculate the motion of objects in space, we take into account the gravitational pull of the sun and the planets. These forces are well understood and highly predictable. Based solely on gravity, we could calculate precisely where Oumuamua ought to be at any given moment. Yet it was moving just a little faster than expected. Something other than gravity appeared to be influencing its motion. This kind of behavior is common for comets. As gas escapes from a comet's surface, it produces a gentle thrust, much like a rocket, causing a small but measurable non-gravitational acceleration. That process is well documented. But Oumuamua had no visible coma. So what exactly was pushing it? Scientists proposed several possibilities. One idea was that Oumuamua was releasing gas in a way that did not carry enough dust to form a detectable coma. Perhaps gas was venting asymmetrically from its surface, generating thrust that we simply could not see. Some observations hinted at extremely faint traces of gas, though the evidence was far from conclusive. Another possibility involved sunlight itself. Every object in the solar system experiences radiation pressure as photons from the sun strike its surface and transfer momentum. For most objects, this effect is negligible compared to gravity. But if an object is extremely thin and relatively light, like a sail or sheet, radiation pressure can become significant. Perhaps Oumuamua was exceptionally thin. Perhaps it was not cigar-shaped at all, but more like a flattened pancake. If it were only a few meters thick, yet hundreds of meters across, and made of a low-density material, then the pressure of sunlight could plausibly account for the observed acceleration. But this idea raises profound questions. How could such a structure form naturally? Why would it be so thin? It is difficult to conceive of known natural processes producing a rigid sheet of rock or ice spanning hundreds of meters. This is where the discussion moves into far more speculative territory. In 2018, two astronomers from Harvard University, Abraham Loeb and Shmuel Bialy, published a paper proposing a provocative idea. They suggested that Oumuamua might not be natural at all. Instead, they proposed it could be an artificial light sail, a thin reflective structure designed to be propelled by starlight. Such a sail could be part of a spacecraft or probe sent across the galaxy by an advanced extraterrestrial civilization. This idea sparked intense debate. The majority of scientists reacted with caution. In astronomy, the notion of aliens is always the final option. You turn to it only after every natural explanation has been tested and found wanting. In the case of Oumuamua, there were natural explanations available, even if some of them felt uncomfortably stretched. Lowe argued that the possibility should not be ignored outright, that it deserved careful consideration rather than dismissal. If Oumuamua were artificial, it would represent the most profound discovery humanity has ever made. The fact that such a scenario seems improbable does not mean it should be rejected without thought. Still, most astronomers remain convinced that Oumuamua was natural, most likely a comet with unusual behavior or an asteroid with an odd geometry, or perhaps a fragment torn from a shattered planet orbiting another star. These explanations rely on fewer assumptions than invoking extraterrestrial technology. The difficulty is that certainty is now beyond our reach. Oumuamua has already departed. It is far too distant and far too faint to observe again. We had only a few brief weeks to study it, and in that short window we could not gather everything we hoped for. When the next interstellar visitor enters the solar system, we will be ready. More telescopes will be watching. Our instruments will capture richer and more precise data. In fact, a second interstellar object was identified in 2019. It is known as Borisov, and this one is unmistakably a comet. It possesses a coma and a tail and behaves exactly as comets within our own solar system do. Borisov is entirely ordinary, and that ordinariness is precisely what makes it remarkable. It shows us that comets from other star systems closely resemble those we know at home, yet Oumuamua remains an exception. Nothing else we have observed quite matches it. Perhaps it was simply an unusual natural object. Perhaps it was something more. We may never know. What is certain is that interstellar objects do pass through our solar system from time to time. The galaxy is filled with asteroids and comets expelled from their parent star systems. They wander through interstellar space, and by chance, some of them cross our path. We now have the capability to detect them, and every one we observe teaches us something new about the universe beyond our own sun. In June of 2018, telescopes across the world detected a brilliant flash in a galaxy 200 million light-years away. It was labeled AT 2018 COW. The name comes from an automated system used to catalogue transient astronomical events. The word COW itself is simply a random sequence of letters, but it has become the shorthand name for this phenomenon. Initially, astronomers assumed it was a supernova. Supernovae are exploding stars, and we observe many of them each year. But as more data arrived, it became clear that AT 2018 COW was different, profoundly different. To begin with, it was extraordinarily bright, between 10 and 100 times brighter than a typical supernova. It also brightened with astonishing speed. Most supernovae take weeks to reach their peak. AT 2018 COW reached maximum brightness in just a few days, and then it faded just as rapidly. Ordinary supernovae remain visible for months, slowly dimming over time. At 2018 COW vanished within weeks. It was as though a cosmic flashlight had been switched on briefly and then snapped off again. Its light spectrum was also strange, failing to match any known type of supernova. The temperatures were extreme, reaching tens of thousands of degrees, and the debris appeared to be expanding at a significant fraction of the speed of light. Astronomers were left perplexed. What kind of explosion could be this? Luminous, this rapid, this hot, and so unlike anything previously observed. It soon became apparent that AT 2018 COW was not unique. By examining archival observations and continuing to scan the sky, researchers uncovered more events of the same kind. These ultra-fast, ultra-bright flashes appear to represent an entirely new category of cosmic phenomenon. They are often called fast blue optical transients, a name that describes them accurately. They rise and fade over days or weeks. They shine blue, producing large amounts of ultraviolet light, a sign of extreme heat, and they are optical transients appearing suddenly in visible light and then disappearing. As of 2025, only a small number have been identified, perhaps a few dozen. They are rare, or at least rarely detected, and their true nature remains uncertain. Several explanations have been proposed. One possibility is that they mark the birth of black holes or neutron stars. When a massive star reaches the end of its life, its core collapses. If the core is sufficiently massive, it becomes a black hole. If it is lighter, it forms a neutron star. This moment of collapse releases an immense amount of energy. Normally, the vast majority of that energy is poured into tearing apart the outer layers of a star, producing what we recognize as a supernova. But there are situations where the energy may escape in a very different way. It could be channeled into a narrow, powerful jet that drills through the star outer layers and then erupts into space. Such a jet would generate a brilliant and extremely rapid flash, a transient event that does not resemble a conventional supernova at all. Another possibility is that these F-bots are created when a star is destroyed by the intense gravity of a black hole. This phenomenon is known as tidal disruption. When a star strays too close to a black hole, the gravitational forces stretch and tear it apart. The stellar debris then spirals inward, heating to extraordinary temperatures and releasing immense amounts of energy. We know that tidal disruption events happen, and we know they can shine with tremendous brightness. However, most tidal disruption events unfold much more slowly than F-bots. They rise to peak brightness and fade away over many months. F-bots, by contrast, evolve at a remarkable pace. One idea is that FBOS represent a rare and extreme form of tidal disruption, where a relatively small black hole pulls apart a white dwarf or a neutron star. In that case, the physics would be very different, and that difference might explain both the speed and the intensity of the light we observe. A third possibility involves violent encounters between compact objects. Imagine a white dwarf colliding with another white dwarf, or perhaps with a neutron star. Such a collision would release an enormous amount of energy in a very short time, producing an F-bot-like flash. The honest answer is that we do not yet know which of these ideas, if any, is correct. FBOs are a very recent discovery, and we are still in the process of understanding their most basic characteristics. Every new detection adds another piece of information and helps us narrow the range of possibilities. What makes FBOS so compelling is that they appear to represent something genuinely new. Astronomers have been studying supernova explosions for centuries. Over that time, we have built detailed theoretical models describing how different kinds of supernova occur. We thought we had a solid grasp of how stars explode. Then in 2018, along came the cow, and it broke all the established rules. It was brighter, faster, and fundamentally different from anything we had anticipated. Its discovery forced astronomers to confront the fact that there are kinds of cosmic explosions we had not even imagined. This is something that happens from time to time in science. You reach a point where you think you understand a phenomenon, and then nature surprises you. You observe something that refuses to fit neatly into your models. That moment is when science becomes truly exciting because it signals that there is something new waiting to be understood. As our telescopes continue to improve, and as we survey larger portions of the sky with greater frequency, we are likely to discover more F-bots. Each one carries clues about its origin. Gradually, by comparing them, we will work out what is driving these extraordinary events. For now, in 2025, they remain among the strangest and most mysterious phenomena we know of in the universe. And now let me introduce you to a star that by all rights should not exist. Its formal designation is HD 14283, but astronomers often refer to it as the Methuselah star after the biblical figure said to have lived for 969 years. This star lies about 190 light-years from Earth. If you know exactly where to look, you can even see it with binoculars shining faintly in the constellation Libra. It is an ancient star classified as a subgiant, which means it has used up the hydrogen fuel in its core and is beginning to move away from the main sequence. Stars at this stage are extremely old. They formed when the universe itself was young and when cosmic conditions were very different from those we see today. By studying such stars, astronomers can uncover clues about the early history of the universe. There are several techniques that allow scientists to estimate how old a star is. One approach focuses on the chemical makeup of the star. The universe began with almost nothing but hydrogen and helium. Heavier elements were forged later inside stars through nuclear fusion and dispersed by supernova explosions. Astronomers refer to these heavier elements as metals, and their abundance increases over cosmic time. A star that contains very few metals likely formed early on before repeated generations of stars had enriched the surrounding gas with heavy elements. The Methuselah star has an exceptionally low metal content. It contains roughly 250 times less iron than the Sunday. That strongly suggests it formed at a very early epoch when the universe was young and heavy elements were scarce. Another way to estimate a star age is to examine how it consumes its nuclear fuel. Stars generate energy by fusing hydrogen into helium in their cores. Once the hydrogen is exhausted, they begin fusing helium into heavier elements. The pace of these reactions depends on the mass and chemical composition of the star. By measuring properties such as temperature, luminosity, and composition, astronomers can estimate how long a star has been burning its fuel, and therefore how old it must be. When these methods were applied to the Methuselah star, the result was deeply unsettling. The calculated age came out to be about 14 billion years, with uncertainties that overlap uncomfortably with the age of the universe itself. And here lies the problem. The universe is only about 13.8 billion years old. This figure comes from several independent lines of evidence, including measurements of the cosmic microwave background, observations of the expansion rate of the universe, and studies of the oldest star clusters. All of them converge on an age of roughly 13.8 billion years. So how can a star appear to be around 14 billion years old in a universe that is only 13.8 billion years old? Technically, the uncertainties allow for an age that is just barely younger than the universe, but the margin is extremely small. It is uncomfortably close. When this result was first reported, some scientists wondered whether our estimate of the age of the universe might be wrong. Perhaps the universe was older than we believed. But as observations improved, the age of the universe became increasingly precise. It is very clearly around 13.8 billion years, with only tiny uncertainties. That means the issue must lie in the way we estimate the star age. But that raises a troubling question. The techniques used to determine stellar ages are well tested and widely trusted. How then could they be leading us astray? They rest on well-established physics and everything hinges on the error bars. The age of the Methuselah star comes out at around 14 billion years, with uncertainties that technically allow it to be as young as 13.7 or 13.8 billion years. That places it just fractionally younger than the universe itself, an extraordinarily tight margin, but one that is still in principle possible. If the star formed very soon after the Big Bang within the first few 100 million years, then it could indeed be that old. Even so, this scenario is deeply uncomfortable. The very first stars were not like the ones we see today. They formed from almost pure hydrogen and helium, with no heavy elements at all. Those primordial stars were likely extremely massive and lived very short lives. The Methuselah star does not resemble a first-generation star. Second-generation stars, which formed from gas enriched by the explosions of the first supernovae, would contain small amounts of heavy elements. The Methuselah star does show a low but measurable presence of heavy elements, exactly what we would expect from a second-generation star. But second-generation stars could not have formed immediately after the Big Bang. Time was required for the first stars to be born, to burn their fuel, to die, and to seed the surrounding space with heavier elements. That process would have taken perhaps a few 100 million years. This implies that the Methuselah star most likely formed at least a few 100 million years after the Big Bang. That places a firm upper limit on its age of around 13.5 billion years or slightly less. And yet the observations persistently suggest an age older than this. Even as measurements have improved and theoretical models have been refined, the estimated age of the star stubbornly remains close to 14 billion years. The troubling part is that the uncertainties have narrowed over time, not widened. Ideally, we would like those error bars to comfortably include a younger age. Instead, they are closing in. So what might be happening? There are several possibilities. One possibility is that our models of stellar evolution are subtly incomplete. Perhaps stars with very low metallicity evolve differently than we currently predict. There may be physical processes affecting nuclear fusion rates that we do not yet fully understand. Another possibility lies in the distance to the star. Determining a star's age depends critically on knowing its luminosity, and luminosity in turn depends on an accurate distance measurement. If the star is slightly nearer or slightly farther away than we believe, its inferred age would change. Astronomers measure the distance to the Methuselah star using parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the backdrop of more distant stars. By measuring this tiny shift, the distance can be calculated. The Gaia satellite has measured parallaxes for billions of stars with extraordinary precision, including the Methuselah star. Even so, a small amount of uncertainty remains. It is possible that the true distance differs just enough from our current value to bring the age estimate down to something less troubling. A third possibility is simply that the star is younger than our best estimate and that we are seeing a statistical outlier. When measurements include uncertainty, the true value can sometimes sit at the very edge of the allowed range. It may be that the Methuselah star is really around 13.5 billion years old and that the 14.5 billion year estimate represents an unfortunate statistical fluctuation. As of 2025, however, the Methuselah star remains uncomfortably old. Astronomers continue to refine their observations, hoping to ease this tension. For now, it stands as one of the more peculiar objects we know, a star that, according to our best measurements, appears to rival the age of the universe itself. Of course, it cannot truly be older than the universe. Something in our measurements or in our models must be slightly wrong. Uncovering exactly what that is takes time, and until it is resolved, the Methuselah star will continue to perplex astronomers. Now consider this. Many of these strange discoveries can seem disconnected at first glance. A mysterious radio signal from the 1970 seconds. a star that dims in irregular ways, vast circular radio structures, enormous cosmic patterns that appear too large, immense empty voids, cold regions imprinted in ancient light, unexpected radioactive elements in a star, an interstellar visitor passing through our solar system, unusual explosions, and an impossibly old star. They appear to be entirely separate puzzles, but perhaps they are not. Perhaps they are all pointing toward the same conclusion, that the universe is more intricate than our current theories suggest, that there are processes, phenomena, or even aspects of physics that we have yet to fully grasp. Think about it carefully. The WOW signal hints at radio sources we do not yet understand. Tabby's star shows us that stars can behave in ways that defy expectation. Giant radio circles reveal that galaxies can sculpt structures we are only beginning to detect. The giant arc and the big ring suggest that the universe may be less uniform than we once believed. The Botez void shows that cosmic emptiness can be more extreme than our models predict. Each mystery on its own is merely an anomaly, something curious that demands explanation. But taken together, they form a pattern. They reveal a universe that continues to surprise us, continuing to challenge our assumptions and reminding us that there is still much left to discover. This is, in truth, entirely familiar within the story of science. When we approach the boundary of understanding, when we are just beginning to glimpse something genuinely new, anomalies appear. Small discrepancies emerge, observations that refuse to sit comfortably within our existing frameworks. At first, they look like minor oddities, isolated curiosities that can be set aside. But then inevitably, someone notices the pattern. Someone realizes that these mismatches are not separate accidents, but expressions of a deeper truth we have yet to grasp. This is precisely how relativity was born. Toward the end of the 19th century, physics was in trouble. Mercury's orbit stubbornly refused to align with prediction. The speed of light appeared to remain constant no matter how it was measured. These issues seemed unrelated technical problems in different corners of physics. Then Einstein arrived and revealed that both arose from a single profound shift in our understanding of space and time. Relativity joined those loose threads into a coherent picture. Perhaps we are witnessing something similar today with these cosmic puzzles. It may be that they are fragments of a larger story. One day, someone may uncover how they interlock, proposing a new theory or identifying a new phenomenon that accounts for them all at once. Or perhaps that moment will never come. Perhaps each mystery stands alone, awaiting its own explanation. The WOW signal might turn out to be a comet. Tabby's star could be surrounded by an unusual veil of dust. Odd radio circles may simply be vast shock waves. The giant arc might be no more than a statistical coincidence. Cybulski's star could host a nuclear process we do not yet understand. We will not know until we investigate. Yet the possibility that these phenomena are connected, that together they hint at something fundamental about the universe, is genuinely thrilling. This is what makes the present era such a remarkable time to study astronomy. And here is something that may surprise you. Many of the greatest advances in our field began with being wrong with observations that directly challenged what we thought we knew. In the early 20th century, astronomers studied distant galaxies and noticed something extraordinary. They were moving away from us. More than that, the farther away a galaxy was, the faster it appeared to recede. This was deeply puzzling. Why would everything be fleeing from our position? Did this place us at the center of the universe? As scientists reflected more carefully, a different realization emerged. This pattern would naturally arise if the universe itself were expanding. If space was stretching, then galaxies would separate from one another, and those at greater distances would seem to move away more rapidly. From this insight emerged the Big Bang theory. The universe began from a single dense state and has been expanding ever since. No one had anticipated this. It directly contradicted the long-held belief that the universe was static and eternal. But the observations left no alternative. Astronomers had to revise their worldview, and that unexpected discovery became the cornerstone of modern cosmology. In the 1960s, astronomers encountered another profound surprise with the discovery of quasars. These objects appeared as tiny points of light star-like in appearance, yet possessing utterly bizarre properties. They shone with an intensity greater than entire galaxies and lay billions of light years away. Nothing in our understanding of stars could explain such brilliance. Eventually, it became clear that quasars were not stars at all. They were the luminous hearts of galaxies powered by supermassive black holes. As matter spiraled into these black holes, it released staggering amounts of energy, producing the brightest sustained light sources in the universe. This realization transformed our understanding of galaxies themselves. We came to see that most large galaxies harbor supermassive black holes at their centers, and that these objects play a decisive role in shaping galactic evolution. None of this was known before quasars forced us to rethink what was physically possible. Then in the 1980s, astronomers studying the expansion of the universe expected to find it slowing down. Gravity, after all, should be pulling everything back together, gradually decelerating the cosmic expansion. But careful measurements using distant supernovae revealed the opposite. The expansion was speeding up. This defied all expectation. What force could possibly be driving the universe apart? From this observation emerged the idea of dark energy, a mysterious component that accounts for roughly 68% of the universe's total energy. We still do not truly understand what dark energy is, but we know it exists because the evidence demands it. Each of these discoveries began with an observation that made no sense, something that contradicted prevailing theories. And each time, rather than dismissing the data or assuming error, astronomers followed the evidence wherever it led. They reshaped their theories to align with reality. That is exactly what is happening now with the mysteries I have described. We are confronted with observations that do not fit within our current understanding. We could ignore them. We could label them as mistakes or statistical accidents. But that is not how science progresses. Instead, we take them seriously. We examine them with care. We work to understand them. And perhaps, just perhaps, they will guide us toward the next great leap in our comprehension of the cosmos. The reason we are uncovering so many strange phenomena in space today is not that the universe has suddenly become more peculiar. It is because our instruments have become more powerful. We are now able to see things that were once hidden from us, and we can measure phenomena that were previously beyond our reach. Consider the so-called WOW signal. It was detected by a radio telescope in 1977. That instrument, known as the Big Ear, was modest by the standards we have today. It was capable of detecting strong radio emissions, but it struggled to determine their precise origin. It also lacked the ability to study those signals in any real depth. Today, our radio telescopes are vastly more powerful. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and the forthcoming Square Kilometer Array, which will become the most sensitive radio telescope ever constructed, have transformed what is possible. These instruments can detect signals that are far fainter. They can locate their sources with extraordinary accuracy. They can examine their structure in remarkable detail. If the WOW signal were detected today, we would learn a great deal more about it. We would know exactly where it originated. We would understand its characteristics with far greater precision. We might even be able to determine what produced it. This is true for all of these cosmic mysteries. We are uncovering them because our tools have improved, and as those tools continue to advance, we will uncover even more. We will also gain a deeper understanding of the phenomena we have already discovered. Tabby's star was identified by the Kepler Space Telescope, which launched in 2009. Kepler was designed to search for exoplanets by detecting the tiny dips in starlight that occur when a planet passes in front of its star. It monitored more than 150,000 stars continuously over several years. Before Kepler, this kind of observation was simply not possible. We had to study stars one at a time, and we could not watch them without interruption. The strange dimming pattern of Tabby's star would have been almost impossible to detect, but Kepler provided continuous data on thousands of stars, and that is how Tabby's star came to our attention. We were not looking for it. We were searching for planets. Yet Kepler's ability to observe stars continuously revealed something entirely unexpected. Today we have the Transiting Exoplanet Survey satellite carrying out similar work. We have the James Webb Space Telescope, which can observe the universe in infrared light with astonishing sensitivity. We also have ground-based telescopes equipped with adaptive optics that allow them to see with a clarity approaching that of space telescopes. Each of these instruments has the potential to uncover something unforeseen. Each one offers a new perspective on the universe, and the more perspectives we have, the more strange and wonderful things we discover. In the years ahead, even more powerful tools are on the way. The extremely large telescope is being built in Chile. When it is completed, it will have a mirror 39 meters across. That is immense. It will be capable of observing extraordinarily faint and distant objects. It will analyze the atmospheres of exoplanets in the search for signs of life. The Square Kilometer Array, when complete, will have a total collecting area of 1 square kilometer. That is roughly 250 acres of radio receivers. It will be 50 times more sensitive than any radio telescope currently in operation. If radio signals like the WOW signal exist, the Square Kilometre Array will detect them. NASA is also planning new space telescopes. Some will search for signs of life on exoplanets. Others will study the early universe. Some will map the distribution of dark matter. Each one carries the possibility of discovering something entirely unexpected. And here is the crucial point. Every time we build a more powerful telescope, we are surprised. Every single time. There has never been an instance where we constructed a more sensitive instrument and found only what we predicted and nothing else. The universe always has something new to show us. That means we can be confident that in the coming decades, we will encounter more strange phenomena, more puzzles to unravel, more observations that do not sit comfortably within our current theories. That is exciting because mysteries are what drive progress. They force us to think more deeply. They compel us to question our assumptions and to develop new ideas. And there is something important to understand about the people who study these mysteries. They are not distant, unreachable geniuses who already have all the answers. They are ordinary people. People who feel a thrill when they encounter something strange. People who stay awake late into the night trying to make sense of confusing data. People who debate fiercely with one another about what the observations really mean. When the WOW signal was first noticed in 1977, an astronomer was reviewing printed sheets of data. The Big Ear telescope recorded its measurements on paper rows of numbers representing signal strength. Most of the time those numbers were low, nothing more than background noise. But on one particular printout there was a sequence of numbers that stood out clearly far higher than the background. The astronomer took a red pen and circled the sequence. Beside it, a single word was written: "Wow." It was a genuine moment of surprise and excitement. That simple human reaction is how the signal received its name. It was not an official label. It was one person's spontaneous response to encountering something unexpected. That sense of wonder, that feeling of surprise, remains at the heart of astronomy today. When Tubby's star was discovered, the scientists studying it were truly perplexed. They knew they were observing something unusual. They worked diligently to explain it. When familiar explanations failed, they were forced to consider more unconventional possibilities, including the idea of an alien megastructure. That suggestion provoked controversy. Many scientists objected. They argued that it was irresponsible to mention extraterrestrial intelligence when natural explanations might still exist. But the researchers were not claiming that it was aliens. They were simply acknowledging that they could not rule it out. And that is an honest position to take when you are confronted with an observation that defies explanation. You have to consider every possibility, including the ones that seem improbable. That is what science feels like from the inside. It is not a polished journey where agreement comes easily and everything fits neatly into place. It is untidy. People disagree. They debate and challenge one another. They argue over how to interpret the evidence. They put forward ideas that later prove to be wrong. Yet within that apparent disorder, progress is always unfolding. Someone makes an observation and others attempt to verify it. Explanations are proposed and then put to the test. Some ideas are discarded. New observations are gathered. Slowly, often painstakingly, a clearer picture begins to form. The scientists studying Zabilski's star have been perplexed for decades. They have suggested many explanations for the radioactive elements found in its atmosphere. None of those explanations fully succeed. And yet they persist. They continue to observe. They refine their thinking. That persistence is the engine of scientific progress. It is the refusal to walk away when things are confusing. It is the decision to keep going, trusting that with enough effort, understanding will eventually emerge. And sometimes that process takes an extraordinary amount of time. The cosmic microwave background was discovered in 1964, but it required decades of observation and analysis before scientists truly grasped what they were seeing. The detailed maps we now have revealing minute variations in temperature came from satellites launched during the 1990 seconds and the 2000s. The cold spot in the cosmic microwave background was first noticed in the early 2000s. It is now 2025. We have been studying it for more than 20 years. We still do not fully understand it, but we have not abandoned the effort. We continue to observe. We continue to think. We continue to search for explanations. That is what science demands. Patience, persistence, and a willingness to live with uncertainty. These qualities do not come easily. It is far more comfortable to have answers than to sit with questions. But the universe is indifferent to our comfort. It simply exists as it is. Our task is to understand it. You might ask why some mysteries remain unsolved for years or even decades. Consider the wow signal detected in 1977. That was almost 50 years ago. Why have we not explained it yet? There are several reasons. In many cases, the fundamental problem is a lack of data. The wow signal lasted for 72 seconds. We have a single data point, one observation. It never appeared again. That makes it extraordinarily difficult to study. Imagine trying to understand an animal after seeing it only once for 72 seconds. You might notice its color, estimate its size, perhaps observe how it moves, but you could not understand its behavior. You would not know what it eats, where it lives, or how it reproduces. A single brief observation imposes severe limits. That is precisely the situation with the wow signal. We have just one observation. Scientists can analyze that signal in great detail, and they have done so. But there is only so much that can be learned from a single data point. What we need are more observations, and so far we have not obtained them. Tabby's star presents a very different challenge. In this case, we have an abundance of data. It has been observed continuously since its discovery. We have seen it dim repeatedly. We have measurements from multiple telescopes across different wavelengths of light, and yet, despite all this information, we still cannot say with certainty what causes the dimming. Here, the issue is not a lack of data. It is the complexity of the phenomenon. Several processes may be occurring at once. The dust hypothesis explains some of the observations, but not all of them. We may need more refined models, additional observations at specific wavelengths, or a deeper theoretical understanding of how dust behaves around stars. With the Methuselah star, the challenge lies in measurement precision. We can measure the star's properties, its temperature, brightness, and composition with remarkable accuracy. We can also estimate its distance with reasonable confidence. But when we combine all this information to determine the star's age, the result appears inconsistent. The difficulty is that the age estimate depends on multiple measurements, each carrying its own uncertainty. When several uncertain measurements are combined, those uncertainties accumulate. It may be that one measurement is slightly incorrect. It may be that our models of stellar evolution contain a small error. Individually, these discrepancies are minor. Together, they can push the age estimate too high. Identifying which measurement is off, or where the models need refinement, is extremely challenging. It requires extraordinarily precise observations and highly detailed theoretical models, and that inevitably takes time. Some mysteries persist simply because they demand technology that does not yet exist. Before space telescopes, many observations were impossible. Earth's atmosphere blocks certain wavelengths of light and distorts others. Space telescopes overcame those limitations. But space telescopes are costly and take many years to design and build. The James Webb Space Telescope was first imagined in the 1,990 seconds, and it finally lifted off in 2021. That is a journey measured in decades, from an initial idea to a machine operating in space. It tells us something important. If answering a cosmic mystery demands a kind of observation that only a new telescope can deliver, then we may simply have to wait for many years while that instrument is designed, built, and launched. Other mysteries endure for a different reason. They wait not for new machines, but for new ideas. At times, we already possess the data, yet we lack the intellectual framework needed to make sense of it. What is required is a fresh perspective, a new way of seeing the problem. These theoretical leaps cannot be planned. They arrive through moments of insight. Creativity does not follow a timetable. You cannot declare that a breakthrough will occur on a Tuesday. It comes when it comes. The discovery of dark energy illustrates this beautifully. In the 1,990 seconds, astronomers observed distant supernovae to measure how quickly the expansion of the universe was slowing. Instead, they uncovered something astonishing. The expansion was accelerating. According to the theories of the time, this result was deeply puzzling. Acceptance did not come quickly. Many researchers suspected errors in the measurements. That skepticism was healthy. But as independent teams collected more observations, the same conclusion kept emerging. The acceleration was real. The universe truly was speeding up. The question then became unavoidable. What could possibly drive this behavior? Existing physics offered no answer. So scientists introduced a new idea. They gave it a name, dark energy. Even today, its nature remains unknown, but naming it allowed it to be studied systematically. That entire journey took years. From the first confusing data through doubt and debate to the recognition that something fundamentally new was required, each stage unfolded slowly as evidence accumulated and theories evolved. The mysteries I have spoken about this evening sit at different points along this path. Some, like the WOW signal, still await further observations. Others, like Tabby Star, are rich in data but demand deeper theoretical insight. Some, like the Methuselah star, require measurements of far greater precision. Others, such as the CMB cold spot, may call for entirely new ways of thinking. Yet all of them are under active investigation. Scientists are watching, measuring, thinking, and arguing. Progress is being made even when it feels slow. In time, these puzzles will be resolved, perhaps not all within our own lifetimes, but eventually. And when they are, they will teach us something profound about how science truly operates. Science is not about possessing all the answers. It is about facing our ignorance with honesty. When we encounter a phenomenon we cannot explain, the scientific response is not to invent a convenient story or to look away. It is to admit uncertainty, to examine the evidence carefully, to weigh multiple explanations, to gather more data, and to think imaginatively about what might be going on. This attitude sets science apart from other ways of understanding the world. In some belief systems, saying "I do not know" is treated as a failure. There is pressure to provide answers even when those answers rest on weak foundations. Science chooses a different path. Acknowledging ignorance is an act of integrity. It marks the beginning of genuine understanding. You cannot solve a problem by denying its existence, nor by accepting an answer simply because it feels reassuring. The WOW signal captures this perfectly. We still do not know what produced it. For nearly 50 years, scientists have been open about that fact. They have suggested many possibilities, from natural radio sources to signals from alien technology to interference from Earth itself. Yet they also admit that none of these explanations is entirely convincing, that openness matters. It ensures that when the true explanation is finally uncovered, it will rest on solid evidence rather than hope or speculation. The same principle applies to every mystery we have discussed. Researchers are forthright about the limits of their understanding. That honesty is not a weakness, it is a strength. It also makes science self-correcting. When errors are discovered, when ideas fail, they are revised or abandoned. Our picture of reality changes in response to evidence. History is filled with such moments. Once we believed Earth sat at the center of the universe. Observations showed otherwise. We once thought the universe was unchanging. Observations revealed its expansion. We once believed nothing could escape a black hole. Theoretical work by Stephen Hawking demonstrated that black holes can slowly evaporate through quantum effects. Each time, the scientific community altered its view in light of new evidence. That is exactly how it should be. Our understanding must evolve as our knowledge grows. The mysteries I have described will almost certainly reshape our view of the cosmos. The changes may be subtle or they may be profound, but whatever emerges will bring us closer to an accurate picture of the universe. That is the aim. Not to defend familiar ideas, not to cling to comforting theories, but to understand reality as it truly is. Even when reality reveals itself as strange, even when it runs counter to what we expect, there is another profound lesson hidden within these mysteries. Technology matters deeply. The instruments we build to observe the universe define what we are capable of discovering. The WOW signal was detected because we had already developed radio telescopes. Before the era of radio astronomy, there was simply no way for us to notice signals of that kind. Entire classes of cosmic radio sources were completely unknown until the middle of the 20th century. Tabby Star was identified only because we built the Kepler Space Telescope with a very specific purpose: to observe thousands of stars continuously over long periods of time. That capability had never existed before. We were unable to monitor so many stars simultaneously, and Kepler fundamentally changed that. Odd radio circles came to light because we constructed ASCAP, a new kind of radio telescope in Australia. ASCAP is able to scan vast regions of the sky rapidly using radio wavelengths. It revealed these circles not because they had suddenly appeared, but because earlier telescopes lacked the sensitivity and coverage needed to see them clearly. The cosmic microwave background was discovered by chance in 1964 when engineers were testing an extremely sensitive radio antenna. They detected a persistent background noise, arriving uniformly from every direction. Initially, they assumed something was wrong with their equipment. Only later did they realize they were observing the faint afterglow of the Big Bang, something that could only be detected with an instrument of such sensitivity. Every advance in technology opens a new window on the universe. Each new instrument uncovers phenomena that were previously hidden from view. We can be confident that future instruments will reveal things we have not yet imagined. This is precisely why investment in scientific instruments is so important. It is not solely about curiosity, valuable though that may be. It is about expanding human knowledge and uncovering new phenomena that may one day have practical applications. Many of the technologies we rely on daily have their origins in astronomical research. The sensors used in digital cameras were developed for space telescopes. Wireless internet technology emerged from research in radio astronomy. Medical imaging techniques such as computed tomography scans are built on principles first developed in X-ray astronomy. When we construct new telescopes, we are not only learning about distant stars and galaxies, we are also developing new technologies that often find their way into everyday life. The mysteries uncovered by these instruments drive further innovation as we attempt to understand them. So investing in astronomy is not merely about satisfying our curiosity about the universe, although that alone would justify it. It is also an investment in technology and innovation that benefits everyone. There is something deeply fascinating about how humans respond to mystery. We are pattern-seeking creatures. Our minds are wired to search for explanations. When we encounter something we cannot explain, it unsettles us. It lingers in our thoughts. We feel compelled to understand it. That is why cosmic mysteries are so compelling. They are real phenomena that we have observed and measured, yet we cannot explain them. This creates a kind of mental itch that demands attention. Consider the wow signal. For almost 50 years, people have asked the same questions. What was it? Where did it come from? Was it natural or artificial? These questions remain unanswered, and that unsettles us. We want clarity. Yet there is something important here. Living with uncertainty, with not knowing, has real value. It keeps us humble. It reminds us that our understanding is incomplete. It stops us from becoming too confident in what we think we know. Throughout history, humans have repeatedly been overly confident. We believed the Earth was flat. We believed it sat at the center of the universe. We believed continents were fixed in place. We believed atoms were the smallest possible units of matter. We were wrong every time. Mysteries like those described here remind us that we may still be wrong about some of the most fundamental aspects of reality. Our current understanding of the universe may be incomplete. There may be major phenomena or governing principles that we have yet to discover. That is not something to fear. It is something to celebrate. It means there is still an enormous amount to learn. The universe still holds secrets. We are not at the end of discovery. We are somewhere in the middle, perhaps even near the beginning. Seen this way, mysteries are not frustrations. They are invitations. Invitations to explore, to discover, to learn. Each mystery points us towards something we do not yet understand, something that once revealed will broaden our view of the cosmos. And so we have spoken about a radio signal that appeared once and then never again. A star that fades in a manner unlike any other we have observed. Vast radio circles surrounding galaxies with no clear explanation. Immense structures in the universe that should not exist according to our current theories. A cosmic void that is almost empty when it ought to be crowded with galaxies. A cold region in the cosmic microwave background that is far too cold to dismiss as chance. A star containing radioactive elements that should have vanished billions of years ago. An interstellar visitor with deeply unusual properties. Explosions that shine brighter and evolve faster than any known kind of supernova. And a star that may be older than the universe itself. These are only a few of the strange discoveries we have made in space. And what is truly remarkable about them is this: they are all real. They are not speculation or abstract ideas. They are direct observations, phenomena we have seen, recorded, and measured. But more than that, they are invitations. Invitations to deepen our understanding of the universe. Invitations to think with greater care, to observe with greater precision, and to imagine possibilities beyond our current assumptions. Each mystery is the universe quietly reminding us that our knowledge is incomplete, and that incompleteness has value. Science begins with observation, and with the desire to explain what we see. When something is observed, we form a hypothesis. We test it. We construct models and derive predictions. When those predictions agree with observation, we gain confidence that we understand what is happening. But there are moments when observations refuse to align with prediction. There are times when the universe presents us with phenomena we simply cannot yet explain. That is when science becomes most exciting. Every mystery described here is an opportunity. It is a chance to learn something genuinely new. Perhaps our models are unfinished. Perhaps there are physical processes in the universe that we have not yet discovered. Perhaps in certain extreme conditions, nature behaves in ways we do not yet fully grasp. History shows us that when theory and observation disagree, it is usually the theory that must change. This is how science moves forward. Newtonian mechanics worked beautifully until we measured objects moving close to the speed of light, and then relativity became necessary. Relativity works extraordinarily well until we reach the quantum realm where quantum mechanics takes over. This does not mean science is flawed. It means science is alive, always refining itself, always improving. Every mystery is a signpost pointing towards something we have not yet understood. The wow signal may reveal natural radio sources we have never encountered before, or it may point to something even more profound. Either way, it is data. Tabby's star shows us that stars can behave in ways we did not anticipate. Whatever causes its dimming, natural or otherwise, it expands our sense of what is possible. Odd radio circles are uncovering structures we did not know existed, revealing that galaxies can be linked to features we are only beginning to perceive. The giant arc and the big ring challenge our assumptions about how uniform the universe truly is. They suggest that on the largest scales, reality may be more intricate than our models predict. The Beats void and the cold spot in the cosmic microwave background test the limits of how structure formed in the early universe and whether our understanding of gravity is complete. Przybylski's star hints that nuclear physics within stellar atmospheres may be more complex than we assumed, or perhaps it points toward exotic forms of matter. Oumuamua opened our eyes to the fact that interstellar objects pass through our solar system, and now we are watching for more. Each one carries information about planetary systems orbiting distant stars. Fast blue optical transients show us that the deaths of stars occur in more diverse ways than we once believed, expanding the catalogue of cosmic explosions. And the Methuselah star reminds us that every measurement and every model carries uncertainty. It keeps us humble. Here is something worth thinking about. We have been seriously studying the universe for perhaps 400 years. Galileo raised his telescope toward the sky in 169, and in that moment, modern astronomy truly began. 4 centuries of careful observation, set against a universe that is 13.8 billion years old. 400 years is essentially nothing. It represents 0.00003% of the age of the cosmos. We have been examining the universe for only the smallest sliver of its existence. And yet within that almost negligible span of time, we have learned an extraordinary amount. We have come to understand what stars really are, how they shine, how they are born from clouds of gas, and how they eventually die. We have discovered that our galaxy is not alone, that the universe is filled with countless other galaxies. We have learned that space itself is expanding. We have detected gravitational waves, revealed the reality of black holes and neutron stars, and identified thousands of planets orbiting other stars. We have traced the vast cosmic web that links galaxies together. We have observed the faint afterglow of the Big Bang, the cosmic microwave background. All of this knowledge has emerged in just 4 centuries. Now imagine what might be uncovered in the next 400 years, or the next 4,000 years, or even the next 4 million. The universe is rich with secrets. Some we have already uncovered. Many more remain concealed. Every new telescope we construct exposes fresh mysteries. Each new part of the spectrum that we learn to observe reveals structures and phenomena we never knew were there. Radio astronomy began in the 1930s. Before that time, we had no idea that the universe was alive with radio sources. Pulsars were invisible to us. Quasars were unknown. The cosmic microwave background itself was hidden. Odd radio circles simply did not exist for us because we had no way to see them. X-ray astronomy emerged in the 1960s. Infrared astronomy followed, then gamma-ray astronomy, and more recently gravitational wave astronomy. Each of these advances opened a new window onto the universe, and each revealed phenomena beyond our imagination. What will we discover with the next generation of telescopes? Which wavelengths remain unexplored? What techniques have yet to be invented? I can guarantee that in 50 years we will understand things that today would sound like pure science fiction. We will have detected phenomena that we cannot even conceive of at this moment. The universe is stranger than we currently know. It may be stranger than we can know with our present technology and understanding. You might ask why any of this should matter. Why care about unusual radio signals, exotic stars, or immense structures far across the universe? These discoveries do not change the fact that you must go to work, pay bills, and deal with everyday challenges. But understanding the universe matters for a deeper reason. It tells us where we stand in existence. It gives us perspective. We live on a planet orbiting an ordinary star within an ordinary galaxy inside a universe that is vast, ancient, and filled with wonders. Some of those wonders we understand, many we do not. And that knowledge subtly reshapes the way you see the world. The problems that feel overwhelming, the disagreements that seem so urgent, all unfold within a cosmos that is mostly empty space and filled with mysteries we barely comprehend. That does not make your problems meaningless. Your life matters. Your experiences are real and valid. Yet there is something liberating about realizing that you are part of something far larger, something strange, beautiful, and endlessly mysterious. Every photon of light that reaches your eye began its journey at a star. It may have come from a star within our own galaxy or from one in a distant galaxy millions or billions of light years away. That light has traveled through space for ages beyond human comprehension. It crossed unimaginable distances, only to end its journey on your retina, allowing you to see. In that moment, you are connected to the cosmos. The atoms that make up your body were forged in stars that died billions of years ago. You are made of stardust, and this is not poetry. It is a literal fact. The carbon, oxygen, nitrogen, and iron within you were created in stars. And now you exist at a time when we can study the universe directly. We can build telescopes, gather data, analyze it, and learn how the cosmos works. We can uncover strange phenomena that challenge what we think we know. We can push the boundaries of knowledge itself. That is a remarkable privilege. For most of human history, people could only look up at the night sky and wonder. They could not measure the distances to stars, detect radio signals, or observe the cosmic microwave background. We can do all of that now, and every strange discovery we make expands the limits of what can be known. One of the greatest challenges in studying the universe is learning to live with questions that do not yet have answers. In everyday life, we have grown accustomed to rapid answers. When a question arises, we reach for a device, and within seconds information appears. We live in an age of immediacy, yet the universe does not share our sense of urgency. Some questions demand decades before they yield anything at all. Others take centuries. Some may never be answered, at least not within the span of our own lives. And that is not a failure. It is one of the reasons science is so deeply compelling. Consider the wow signal once more. Nearly 50 years have passed, and we still do not know what produced it. That uncertainty can feel uncomfortable, even irritating. But it also reminds us that the cosmos unfolds according to its own rhythm, not ours. We cannot insist on explanations. We have to wait for the right observations, the right instruments, and the right ideas to emerge. That waiting has value. It cultivates humility. It reminds us that understanding is not something we are owed on demand. The universe is under no obligation to be clear on our timetable. And during the waiting, something important happens. We learn other things. We build new technologies. We educate new generations of scientists. We make observations that may not resolve the original mystery, yet they uncover something else entirely unexpected. Science is filled with discoveries made by accident found while we were searching for something different. The cosmic microwave background was discovered by accident. Pulsars were discovered by accident. Penicillin was discovered by accident. So, while we continue to puzzle over the wow signal or Tabby's star or any of these enduring mysteries, we are also engaged in other work making other discoveries, expanding knowledge in ways we did not anticipate. The mysteries matter, but they are not the only thing we do. This is something that can be difficult for those outside science to appreciate. It can appear as though time is being wasted on problems that refuse to yield answers. Why spend decades studying something that resists explanation? Why not turn instead to simpler questions? Yet the problems that seem unsolvable often become solvable in time. And even when they do not, the attempt itself teaches us. It drives the development of new methods, sharpens our thinking, and reveals phenomena we did not expect to find. Take the search for dark matter. We have not yet detected dark matter particles. Decades of effort, billions of dollars invested, and still no definitive signal. To some, this looks like failure. It is not. The experiments built to search for dark matter have transformed particle physics, advanced detector technology, and eliminated vast ranges of theoretical possibilities. Even searches that do not succeed deliver knowledge. The same is true of these cosmic enigmas. Even if we never learn what caused the wow signal, the effort to understand it has pushed radio astronomy forward, refined how we analyze signals, and forced us to think carefully about what genuine evidence for extraterrestrial intelligence would actually look like. Tabby's star has shown us that stars are more complex than we once believed. It has revealed behaviors we did not predict and highlighted the need for better models of how dust interacts with starlight, even if its dimming is never fully explained. The attempt itself has been instructive. Science is not only about answers, it is about asking meaningful questions, creating ways to explore them, and following the evidence wherever it leads. Mysteries are not obstacles, they are opportunities. We are nowhere near the end of discovery. Astronomy is still young. We have barely begun to explore what is out there. The universe contains far more than we have yet observed. Future telescopes will be more sensitive. They will survey more of the sky more frequently across more wavelengths. They will detect fainter signals and objects at greater distances. Every new observation carries the possibility of surprise. Perhaps one day we will finally understand the wow signal. Perhaps we will detect another like it. Perhaps we will find clear evidence of intelligent life elsewhere in the universe. Or perhaps we will discover that we are alone, a conclusion that would be just as profound. Perhaps we will uncover the cause of the dimming of Tabby's star. Perhaps we will find many more like it. Perhaps we will identify an entirely new class of stellar behavior. Perhaps we will come to understand odd radio circles. Perhaps they will teach us about galaxy evolution, or supermassive black holes, or something we have not yet imagined. Perhaps we will find even larger cosmic structures that challenge the cosmological principle, forcing us to rethink how the universe is organized on its largest scales. Perhaps we will resolve the mystery of the CMB cold spot. Perhaps it will indeed be a super void, or perhaps it will point towards something far more exotic. Perhaps we will understand Sibylski's star. Perhaps it will open doors to new insights in nuclear physics, or reveal unfamiliar aspects of how stars function. Perhaps we will detect more interstellar visitors like Oumuamua. Perhaps in time our observations will sharpen and the data will grow clearer. Perhaps one of these signals will reveal itself as unmistakably artificial. Or perhaps every single one will prove to be natural, offering us deeper insight into how planetary systems form and evolve around distant stars. Perhaps we will finally grasp the nature of fast blue optical transients. Perhaps they will illuminate the processes behind black hole formation, the lives of neutron stars, or the violence of stellar collisions. And perhaps we will settle the question of the age of the Methuselah star. Perhaps our theoretical models will mature, or our measurements will become precise enough that the tension simply dissolves. Or perhaps we will uncover entirely new puzzles, things beyond our current imagination, phenomena that will confound future generations of astronomers, just as these mysteries challenge us today. That is the beauty of science. It is a continuous journey. We are not seeking to possess every answer. We are striving to ask better questions. We are pushing against the edges of what we know and what we understand. So tonight, when you step outside, pause for a moment and look up. Look at the stars. Consider that some of those tiny points of light are not stars at all, but galaxies, vast collections of billions of suns lying millions of light years away. Reflect on the fact that somewhere in that immense cosmic ocean, a star is dimming in ways we cannot yet explain. There is a region of space that is almost completely empty. There is a signal that appeared once and then vanished. There is an interstellar object racing silently through the darkness. There are explosions brighter than we ever believed possible. There are structures larger than our theories say should exist. The universe is strange. It is filled with mysteries, and every mystery is an invitation. An invitation to wonder, to question, to explore. We are fortunate to be alive in an era when we can study these phenomena, when our telescopes are powerful enough to detect them, when our knowledge and technology allow us to recognize that something truly unusual is happening. 400 years ago, none of this could have been imagined. 400 years from now, we will know vastly more than we do today. But right now, in this moment, we stand at the frontier. We are pressing outward, discovering strange things in space and trying to understand what they mean. That is an extraordinary privilege, and it is unfolding right now. Not in some distant future, not in a work of science fiction, right now within our own lifetime. So when you gaze up at the night sky, remember that you are looking into a universe overflowing with wonders. Some we understand, many we do not. And every strange discovery reminds us that the cosmos is far richer and more surprising than we ever imagined. The journey of discovery goes on, the mysteries persist, and somewhere out there in the vast darkness between the stars there are strange things waiting to be found. things that will confuse us, test us, and ultimately teach us something new about the universe we inhabit. That is what makes astronomy so thrilling. That is why scientists stay awake late into the night studying data, building models, and attempting to explain what currently defies explanation. Because the universe is strange and strangeness is wonderful. Let me leave you with one final thought. Every mystery I have mentioned tonight refers to something real, something that exists out there right now. The wow signal happened. Tabby's star is dimming. Odd radio circles exist. These are not abstract ideas. They are observations. And that has a profound implication. The universe does not care about our theories. It does not care about our models or our expectations. It simply behaves as it does. And when we observe it carefully, it reveals things that surprise us. That is both humbling and exhilarating. Humbling because it reminds us how much we have yet to learn. Exhilarating because it guarantees that there is always more to discover. Science is not about having all the answers. It is about being honest about what we do not know. It is about examining the evidence and admitting when we are puzzled. The scientists investigating these strange phenomena are not embarrassed by the absence of explanations. They are energized by it, because mysteries are opportunities. Every unsolved question is a chance to uncover something fundamental about how the universe truly works. Perhaps some of these mysteries will be resolved soon. Perhaps others will remain unsolved for decades or even centuries. Some things may never be fully explained, and that is perfectly all right. The universe does not exist to provide us with simple answers. It simply is. Our role is to watch it with care, to measure it with rigor, and to try to comprehend it as deeply as we can. And when we reach the limits of our understanding, we must be honest enough to say so, to say that we do not yet know. We continue observing, we continue measuring, we continue thinking, because that is how progress is made, not by claiming certainty where none exists, but by openly acknowledging the gaps in our knowledge. The most peculiar discoveries we have made in space are peculiar precisely because they sit outside what we currently understand. They refuse to fit neatly into our theories. They stand apart as exceptions. They are anomalies. They are riddles waiting to be unraveled, and riddles can be solved. Perhaps not today, perhaps not tomorrow, but in time, with patience, careful observation, and sustained thought, clarity emerges. That is the narrative of science. A long unfolding of mysteries gradually resolved, revealing a universe far stranger and far more beautiful than we ever anticipated. So when you next hear of an odd discovery in space, do not see it as a failure or a problem. See it as an invitation to learn something new, an invitation to push the boundaries of what we know, because the universe is rich with strangeness. Some of it we have already uncovered, and much more remains hidden. And every discovery, when it comes, teaches us something profound. This is the adventure of astronomy. This is why people devote their lives to studying the cosmos. Because out there, in the vast darkness between the stars, mysteries are waiting. Unusual signals, stars that fade without warning, enormous circles, structures that seem impossible, ancient voids, cold regions in space, radioactive elements that should not be there, visitors from beyond our solar system, unexplained bursts of energy, stars that appear older than the universe itself. These are the phenomena that keep astronomers awake at night, not out of fear but out of wonder. And if you have followed these strange stories to this point, perhaps you feel that sense of wonder too. That is a good thing. The universe merits our fascination. It calls for our curiosity. It deserves our most determined efforts to understand it, precisely because it is strange, beautifully and profoundly strange. And it is that very strangeness that makes it worth studying. This journey through the most extraordinary discoveries in space is a reminder of how much there is still to learn. The universe is filled with mysteries, and we have only just begun to grasp its nature. There are remarkable things waiting to be discovered, things that will confuse us and astonish us, things that will challenge what we think we know. That is not a cause for concern. It is a promise. The universe is strange, and we are fortunate to be here to witness it. Rest beneath the stars, and remember that somewhere out there, extraordinary things are unfolding. Things we do not yet understand. Things that may one day transform everything we know about the cosmos. Good night.